Hello, George Romanic here. In today's video we are going to put together our knowledge from previous videos and go back to Boltzmann distribution of energies to derive the expression for a Lagrange multiplier. You might ask, why did it take so many videos to do that? The answer is because kinetic theory of gases and statistical mechanics in general are complicated topics. Yes, we did derive Boltzmann distribution of energies, and we even showed how it looks like graphically and discussed it. But yet there was that Lagrange multiplier that stayed unknown. And to properly find the expression for Lagrange multiplier, we had to go on a D route and describe few mathematical concepts, namely solve Gaussian integral and some integral that looks like Gaussian, but it's not quite Gaussian. Now we did that homework and we can go back to Boltzmann distribution and find that Lagrange multiplier. I wanted to do it the right way. In many other instances, namely some channels would tell you that Lagrange multiplier is proportional to 1 over T, where T is absolute temperature, and then they would tell you it can be demonstrated it's actually equal to 1 divided by KT, where K is Boltzmann distribution, T is absolute temperature. But I don't want to tell you it's that. I want to show you that Lagrange multiplier is that. And to show you explicitly, we had to have these mathematics videos. But now we have everything that we need to go back and find the expression for a Lagrange multiplier. Let's do it. Our previous videos derived that Boltzmann distribution has this form, where this capital P subscript I is probability of finding an atom in ith energy state. Ni is the number of atoms in the ith energy state, N is total number of atoms, epsilon I is the energy of the ith energy state, and lambda 2 is that unknown Lagrange multiplier. And I will tell you right away what all YouTube channels tell you, that lambda 2 is equal 1 over k times t, and they tell you it can be demonstrated. On this channel, in this video, we will demonstrate this explicitly. As we demonstrated in my video on Boltzmann distribution, we see that probability Pi is an exponentially decreasing function of energy. To find this unknown Lagrange multiplier lambda 2, we will start with the energy constraint that we described in my previous videos. And the energy constraint says that sum over all states Ni epsilon I is equal capital E, where capital E is total energy of the gas. Basically what we are saying here, let's assume we have some volume of gas and we have this many particles with energy level that corresponds to this purple color. We have this many particles with energy levels that correspond to these pink energy levels, and maybe, just for good measure, this many particles that correspond to blue energy levels. Now this equation tells you number of blue times energy of blue plus number of purple times energy of purple plus number of pink times energy of pink is of course total energy of this gas, and that is more than logical. Now what we will do, we will divide this equation by capital N, which is total number of these particles, and we will get that sum Ni over N, and I can move N under the sum because it's a constant, times epsilon I is equal total energy divided by N. But this total energy divided by N is simply average energy per particle, and Ni divided by N is this probability. So we can see that one can easily write that this constraint, energy constraint, is capital P I epsilon I is equal average energy. Now let me go back to this gas and identify a particle. Let's take this one. And let's say this particle has this momentum. This is now momentum small p, not capital P. Capital P is probability. If I take this to be my x direction, then you will see that momentum in the x direction of this particle is this px. So what is momentum in the x direction? Well, momentum in the x direction is mass times velocity in the x direction, where m is the mass of this particle and vx is component of velocity in the x direction. So that means, using this concept over here and this equation over here, I can rewrite this equation in terms of x direction, namely sum of capital P, again, probability of finding particle in energy level I times energy of that level I in the x direction is equal average total energy but in the x direction. That's very simple. But we know that this energy is kinetic energy of motion of these atoms. So epsilon x would really be 1 over 2 mvx squared. That's simple formula for kinetic energy. But now I can combine these two formulas for momentum and kinetic energy to get that epsilon x is equal 1 over 2. What else do I get? I get mass downstairs and here px squared. With this formula, I can substitute that expression into my Boltzmann distribution to get that probability, again, capital P, of px, momentum in the x direction, is equal e to negative lambda 2, and here I have px squared divided by 2m, and here I have sum over all states e to negative lambda 2 px squared divided by 2m. And what is this expression? This is now important conceptual part. This expression gives us probability that a given atom will have momentum in the range px to px plus dpx. We have to define range with the width of dpx because momentum is continuous variable, and therefore probability of any given particular momentum is 0. And you know that from mathematical statistics, when you have a distribution function that is continuous, I don't know, let's say it looks like this. So this is probability function f of x, and the probability to get any particular value of x is 0 because this is continuous function. So you always have to define interval, and the width of this stripe, of this interval, is x to x plus dx, namely width is dx. And then you can find probability of that interval, but never any given value of your independent variable or random variable. Well, because momentum, therefore, because momentum is continuous variable, that also means we have to go from sum to integral, because integral is continuous summation and sum is discrete summation. Okay, so our denominator over here will be sum over all states e to negative lambda 2 px squared divided by 2m is equal to integral. Now all states, well, that means momentum can go from negative infinity to positive infinity. E to negative lambda 2 px squared over 2m dpx. Perhaps some of you are looking at this integral saying, oh my god, now we need to solve this. No, because I solved this integral in my video on Gaussian integral. Notice that this is nothing else but Gaussian integral, because lambda 2 and 2m are just some constant. And the solution of this integral, based on my video on Gaussian integral, is simply 2m pi divided by lambda 2. Which means that we can write this probability as probability is equal square root 2m pi divided by lambda 2. Because this is in denominator, I have to reverse it. So this is equal square root reversed lambda 2 divided by 2m pi, and then nominator e to negative lambda 2 px squared divided by 2m. How do we deal with this term over here? Well, this is a beautiful part also. From my video on temperature of a gas, we saw that temperature is related to average kinetic energy of particles in the gas, in a way that this average kinetic energy 1 over 2m Vx squared is equal 1 over 2 kT, where k is Boltzmann constant that I defined at the beginning of the video, and T is absolute temperature. This, as you can see, is further equal average energy in the x direction, average kinetic energy in the x direction. But notice that here we already related average kinetic energy in the x direction with probability and energy levels. So if we go back here, I can write that this 1 over 2 kT is equal sum over pi, again this is capital P, probability, epsilon I in the x direction. And this sum is over all states again. And now I do the same trick as before, namely, instead of epsilon ix, I substitute this over here, just as I did in this denominator case, and sum over all states has to become integral from negative infinity to positive infinity, which will give us that this left hand side 1 over 2 kT is equal integral from negative infinity to positive infinity px squared divided by 2m times, so this is my epsilon ix as I demonstrated above, and then times this over here, and that is square root lambda 2 divided by 2m times pi e to negative lambda 2 px squared over 2m dpx. Now we can make this big expression look a little bit nicer and write 1 over 2 kt is equal. This is one big constant. This square root together with this 2m is one big constant, so I will write square root of lambda 2 divided by 2m square root 2m 2 pi m. And then I have this integral from negative infinity to infinity, px squared, that's this one, and this exponential function over here. Perhaps again some of you are saying, oh my god, some crazy integral. No, I solved this integral explicitly in my previous video, and this is integral that you can see looks like Gaussian integral if we don't have this over here. Then this is perfectly Gaussian integral. But we do have this term over here, and I taught you how to solve it using integration by parts. The solution of this integral that we demonstrated in my previous video is square root of 2 pi m to power 3 over 2 divided by lambda 2 to power 3 over 2. Go back to my previous video to convince yourself. Now I can write therefore 1 over 2 kt is equal square root lambda 2 over 2m square root 2 pi m and times this over here 2 pi m 3 over 2 divided by lambda 2 to power 3 over 2. Now notice that this 2 and this 2 can cancel. Square root of 2 pi can cancel with this 2 pi over here. And I will have here that kt is equal. When you are dealing with this mess like that, try to put everything in terms of powers. What do I mean by that? Write this square root as lambda 2 to power 1 over 2. This m as m to power negative 1. Now we have this m, that would be m to power negative 1 over 2. And then we have this m to power 3 over 2. And we have this lambda 2 to power negative 3 over 2. And now this is, as you can see, easy, because these 3 will give me, so this will be m to power 0, because I just add minus 1 over 2 plus 3 over 2, that is 0, which means this over here is 1, because anything raised to 0 is 1. And clearly, lambda 2 will be 1 over 2 minus 3 over 2. So for lambda 2, I will get that combination of these two is lambda 2 to power negative 1. Or kt is equal 1 over lambda 2, and that means lambda 2 is equal 1 over kt. And this is by far the cleanest derivation of unknown Lagrange multiplier in Boltzmann distribution. Nothing here was assumed. These integrals were explicitly solved in my previous videos. Boltzmann distribution was explicitly derived and discussed in my previous videos, and now everything was brought together to clearly demonstrate how Lagrange multiplier is equal 1 divided by Boltzmann constant times absolute temperature in kelvins. With this beautiful knowledge in mind, we can write that our probability Pi to find particle in the ith energy state, which is number of atoms in that energy state divided by the total number of atoms, is e to negative epsilon I divided by kT. Finally, we are using temperature and not Lagrange multiplier, sum over all states, e to negative epsilon I divided by kT. So this is probability form of Boltzmann law, or you can write it in the terms of the number of atoms by Ni, number of atoms in ith energy state, becomes total number of atoms times e to negative epsilon I kT divided by the sum over all states, e to negative epsilon I times kT. In principle, there is nothing else a person could say in terms of derivation of Boltzmann law. We derived it and we determined unknown Lagrange multiplier. At the very end, I would like to show you something beautiful that you can now take from this video and apply to perhaps atoms in your room. You cannot see those atoms, but you can imagine the result that I will show you here. If we take a ratio of probabilities of two states, that would be, for example, ratio of probability of state I to probability of some state j, then we would get that here we have e to negative epsilon I over kT, and here we have this sum term, and in denominator we have the same for the j state, so we would have e to negative epsilon j over kT over this sum term. But these sum terms, I told you before, they are constants. So this cancels with this, which means that this results in being e to power epsilon j minus epsilon I divided by kT. Now, what this beautiful result is telling us? Well, first of all, this over here is known as Boltzmann factor, and it is telling us that the ratio of probabilities only depends on states' energy difference and the temperature of the gas. So we can see from here, if epsilon j minus epsilon I increases, namely if the separation between energy states increases, logically ratio of probabilities of finding atoms in these states increases. That makes sense. But we also see if temperature increases, then this ratio decreases, which means at higher temperatures, energy levels are closer to each other. And I prepared a nice graph to demonstrate this for you. Here we have number of atoms as a function of energy levels. Blue curve corresponds to temperature T1, red curve to temperature T2. You have to know that area under these two curves are the same. Both of them correspond to Boltzmann distribution that is normalized. and all that beautiful stuff that we talked in previous videos. But look at this beauty. T2 is 5 times T1. And I told you, when temperature is low, and that's blue curve, you have big separation between energy states. As you can see, big separation between here and let's say here. Big separation. As you increase temperature, separation between energy levels decreases. The separation is much smaller. Boltzmann distribution of energies is one of the most beautiful laws in physics. It took many great men to figure out this theory. First it was Gay-Lussac, it was Boyle, it was Mariotte, Avogadro, Graham and so on, that experimentally figured out that there is some relationship between temperature, pressure, volume of ideal gases. But then, many decades later, it was the greats of Maxwell and Boltzmann, and Einstein also contributed to the development of theoretical concepts of kinetic theory of gases. All them together contributed to what we see today as this great theory. This theory is extraordinarily amazing, and that's because it is enabling us to visualize something that we will never be able to see with our own eyes. You sit maybe in some room, car, basement, park, and there is air around you. Our eyes will never be able to see atoms and molecules, but thanks to kinetic theory of gases, we can visualize what is happening in the air around us. You can visualize how atoms have different energies, and these different energies are not distributed in any way, but this way, and this way is Boltzmann distribution of energies. It is absolutely breathtaking theory. Now we will move forward, and forward is Maxwell-Boltzmann distribution of speeds. Equally amazing theory. We will use Boltzmann distribution of energies and move from energies into velocity space. And then once again, you will be able to visualize something that your eyes will never be able to see, as well as my eyes, especially my eyes, because I don't have very good eye vision. But what I'm talking about is, of course, distribution of speeds. Nitrogen, it's 78% of air that we breathe. We will never be able to see atoms of nitrogen in air. But next few videos and Maxwell-Boltzmann distribution will help us to visualize how speeds in that nitrogen are distributed in these atoms of nitrogen. You will see that atoms of nitrogen around you and me are flying through space at speeds of approximately 700 meters per second or higher. Think about it. Think about speed of 700 meters per second. It's 2 times higher than speed of sound. We will see that in 1 cubic meter, in 1 second, there are over 10 to power 34 collisions of atoms. 1, 2, 3, 4, 5, you count seconds. And you imagine 1 cubic meter of air. In that cubic meter, there are more than 10 to power 34 collisions of atoms. We will never be able to see that, unfortunately, but thanks to Maxwell, Boltzmann, and all these great men that I mentioned, we can visualize it properly using kinetic theory of gases, Boltzmann distribution, and Maxwell-Boltzmann distribution of speeds that we will now tackle in next videos. So stay tuned because great content is coming up. Until then, goodbye.